Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Alrighty, let's make a start. So, all my praying overnight has worked, and it looks like everything's actually working. So here we are, week 6, and things are working. Nice. All right, let's start with some fun. Graphics don't have to be serious, do they? Right? So this is a website called GraphJam. You know it's going to be fun because the URL is memebase.cheeseburger.com. So hey, you know, they produce a lot of graphics that are basically jokes, and they're mostly bar charts and pie charts, but always pretty funny. So you know how to scare kids now. You know, monsters, threats, have stuff lying around your room, or confiscate their internet. You can see that's most of it. Everyone's friends are jerks. So why I have a password on my phone? Yeah, to protect my personal information, and then so my friends won't post to Facebook as me. It's pretty much correct. I don't know what that one is. That's weird. What's this one? The Wheel of College. Here we go. Oh yes, looks like Wheel of Fortune. Very good. Trying to find a bar chart here somewhere. Oh, it's a line chart. Okay. Don't get that one. What I'm thinking about while playing hide and seek. Yeah, I hope they don't find me. OMFG, I guess you know what that means. A spider. And then why am I breathing so loud? And so on. They're all pie charts. Oh dear. Anyway, they go on for pages and pages and pages, right? So, oh, there we go. This is a Venn diagram. Buying PC games, fun to play. And then, of course, my computer can't handle it is what happens every time you buy a computer game. Here's a bar chart. This is cool. This is cool. We've come so far. It's a bar chart of mobile phones down through the ages. Who owned any of these, apart from that one? I think I get back to here. I never owned one of these. Oh my goodness. So yeah, all good. Anyway, bit of fun. All right, babies. Okay, so yesterday we started talking about this baby data, and we've got quite a journey to go on because it's high dimensional, right? We've got 6 dimensions that we're interested in. The response variable is survival. It's a binary response, okay? So, you know, most of you have come here through maybe a first year stats class, maybe regression modelling. That'll probably be where you max out. Anyone here done survival models in the actuarial program? One person? Okay. So you might have seen a survival model using a logistic regression or something like it, but most of you won't necessarily have seen logistic regression. So logistic regression is where you model a binary response against covariates, and you do so using usually a logit link. It's a generalised linear model. Okay? But if you haven't done that course, that's not going to make any sense to you. You can't just fit a regression model to this, a standard regression model, without doing anything because your response is a 0 or a 1. It's binary. And predicting zeros and ones using a continuous model, if you just let the zeros and ones be your response, pretty damn hard. Okay? So we're going to start by pursuing a non-modelling approach. We're going to try and look at this visually. Now the immediate challenge is you're in 6 dimensions. You can't visualise 6 dimensions. You just can't. You max out at 3. Right? Einstein maxed out at 4, and because time is a dimension, right? And he's smarter than all of us here. So, you know, once you go beyond 3 dimensions, that's it. Visualisation becomes very hard. Okay. Now, a scatterplot matrix, which is the thing we've got in front of us here, is a very, well, pathetic, probably, attempt to visualise 6 dimensions. You visualise the 6 dimensions by looking in every obvious 2-dimensional subspace, okay? Now, there are infinitely many two-dimensional subspaces in this data, right? You're looking at precisely, well, we can count them, 15 directions out of infinitely many. And you're hoping that those directions are the interesting and meaningful ones. That is like finding a needle in a haystack, right? So scatterplot matrices will only take you so far. They tell you about all the two-dimensional relationships within this six-dimensional space. But one of the things we'll very quickly discover is that 6D space is not composed of 2D relationships that you can put back together, okay? It just isn't. And so this is our first and relatively vain attempt to reduce dimension. So it's a 2D plot, but it's showing me every 2D relationship among the 6 dimensions. Some of the relationships are obvious. For instance, weight and age. There's a relationship here. It doesn't necessarily look linear. It doesn't even necessarily look homoscedastic, but it's clear that the lower the gestational age, in other words, the shorter the time that the baby's inside mum, the lower weight it comes out. But, you know, that's not universally so, right? Here's a baby, this one right here, very low gestational age, but a relatively heavy baby, right? So, I don't know what's going on there. This one probably even worse, right? So I think, you know, up in this part of the chart, childbirth's going to be pretty hard. And down here, you're like, well, the baby's only been in for 20 odd weeks, and oh my God, right? So then you've got these sorts of cases down here, right? Very low weight babies who've been in a relatively long time, okay? And this is just the normal variation that occurs, right? So, but there's a relationship there, and you can sort of see roughly what it is. There's a relationship here between 1 minute APGARs and 5 minute APGARs. So the way you read this plot, by the way, is you basically pick any panel, and then the horizontal variable is the variable listed immediately above or below it, and the vertical variable is the variable listed immediately to its side or left or right. There's a relationship here. Generally speaking, if you have a high 1 minute APGARs, you're going to probably have a high 5 minute APGARs. But again, it's not universally so. Here we have a baby who had a relatively low, in fact a very low, 1 minute APGARs. So basically at birth, not viable is what the doctor would say. So if you've got a 1 minute APGAR that's down around 1, not breathing, possibly blue, signs are very bad. But at 5 minutes, this baby was up to about 6 or 7, right? So that first 5 minutes of life for that baby was pretty important, right? Then you've got babies that are sort of on this side here, okay? High 1 minute APGARs, doing okay initially, but then it went down, right? So this is a baby whose first 5 minutes of life was probably not so good. So lots of variation here. The other thing you'll notice about this particular plot is that it's on a grid. And that's because the 1 minute APGARs and the 5 minute APGARs are discrete variables, right? They're 0 to 9. Okay, so that's on a grid. What else can we see? It looks like weight is related to 1 minute APGAR, but the relationship is very dispersed. Similarly, it's related to 5 minute APGARs, same comment. Does not appear to be related to blood pH at all. You don't see any relationship here, nor here. In fact, it doesn't look like blood pH has much to say at all. Now, all we've done so far is we looked at the covariates, the variates that we measure but which don't necessarily govern the question we want to ask. And the question we want to ask is this baby going to survive? And that data's up here. Now, trying to find the relationship between this variable and weight and age and APGARs and so on is pretty hard, right? You might make the observation in this first plot here that it looks like these points are sort of further to the left. So low weight tends to bring low survival. You might make the observation that these points here are a little bit shifted to the right, so high weight brings higher survival. But there's so much overlap. And these are so variant, have such high variance that you couldn't make any really reliable prediction. And when you look at age, you can't tell anything really. Okay, the APGARs are useless essentially because of the gridding. You might make the judgment that because there's one dot here and one dot here, and they ain't one dot, by the way, it's multiple dots all on top of each other, that this goes roughly up, and this one here, who knows. So what we very often want to do, and I'll show you how to do it, is augment this plot with some lines within each panel, just to give you some guidance beyond the mere points. So the way you do that is you use the pairs function. So pairs is the function that produces a scatter plot matrix. And then if you use the panel option to that pairs function, you can tell within each panel, you can tell R what to do. Okay? So we go pairs of baby, panel equals, and then we say, okay, we want to do this inside the panel. We wanted to do two things. We want to put the points in the panel, points x, y, and we want to add a low S curve to the panel. Okay? And you do that within a function, so you do both of them. All right? And this is what you get. Now this is really interesting, because suddenly what you sort of could see just by using your mind to, or your eyes literally, to see patterns, you can see those patterns play out. You can see the relationship between weight and age. You can see the relationship between the two APGAR scores. There does not appear to be a relationship with blood pH between weight and blood pH and age and blood pH, but some mild relationship with the APGARs. But here's the row of plots that's really interesting. This is a low S curve that's trying to fit to the survival panel, and you can see, yes, it does seem to go up when weight goes up, right? So low S helps you here see a relationship. Same with age, same with both of the APGARs. The blood pH is fascinating. It goes up and then drops, and this kind of makes sense too if you think about it. You know, pH, if pH is too low, you've got alkaline blood. If pH is too high, you've got acidic blood. Neither of those sounds very good. It turns out, in terms of survival, somewhere in the middle is probably about right, and so this curve comes up and peaks and then drops. So these relationships kind of make sense, and if you have a good imagination and you look at, say, these two pictures here, this might remind you of a logistic curve. Okay, if you've seen one of those before, logistic curves looks like an S. Okay, that could be accidental, right? You know, a logistic curve basically goes up, these go up, so it has that resemblance, but that might be some post-justification for fitting a logistic regression, if that's what you wanted to do. It's not where we're going with this, but, you know. So this is a pretty good attempt now to summarise this data, and probably the best you can do to look at a lot of relationships very quickly. One of the things that I'll point out about scatterplot matrices is they use the principle of small multiples, right? Small multiples in a graphic have lots of little panels or lots of little subgraphs that you can look from one to the other and compare, okay? It makes comparison easy. And remember, being able to compare things is very important, okay? Happens every day, doesn't it? There you go, the fireys. Excellent. Okay, at least they're not going to the CPE building like normal, yeah.
Aren't they mirror imaging?
Yes, yes. So some packages produce only the upper half or the lower half. R produces both sides. The reason we're looking at the top half only is because survival's our response.
But if you look at the top corner and the bottom corner,
Yeah.
they have a different graph?
Yes, they do. Well, yes and no. The points are in the same spot. The line's different because in the top half of the graph, it's using least squares to minimise distance in the vertical direction, and in the lower part of the graph, it's minimising horizontal distances, which is something we don't want to do, typically. So that's why they look different. So yeah, it's if you ever look at an XY plot and you fit least squares both in the X and in the Y, you get two completely different lines typically. And that's because X and Y, they're optimising in different directions. That's what's going on. So we're only interested here. So the question you've asked raises a very good point, which is which one do you look at, top half or the bottom half? Find your response variable. Whenever your response variable is the vertical variable, that's the half you're going to look at, because that's the half that sort of makes the most sense in the context that we're interested in. Okay, so that's our first attempt. Now, we're going to try to do dimension reduction in a few different ways, and you know, we're kind of stuck in 2D, right? I mean, we could entertain some 3D kinds of graphs, but, you know, again, is there much point going to 3D when you've actually got 6D? I mean, what are you really buying for yourself? We will have a brief look at it a little bit later, but just for the moment, we're kind of, you know, 2 dimensions, 3 dimensions, not much better. So what we're going to try to do is find 2-dimensional plots that preserve as much of the information as we can, right, while allowing us to see an insight into the full 6 dimensions. So here's a first attempt at that. Now, I'm going to show you the plot first. The R is a little bit complicated. We'll go back through the R, okay? So, but first I want to show you and talk about the plot. So there's the plot. And then I'll show you the R that produces it and why that works. So this is a plot where we've plotted age versus weight. So age is your X variable, weight is your Y variable. But inside the plot, I've used different symbols, and those symbols encode the other variables, okay? Most of the other variables, not all of them. Now, here I've got some luck. The luck is that my response variable is binary. It's a 0 or a 1. And so I can use an empty symbol when survival is 0 and a filled symbol when survival is 1. And I get a really nice high contrast picture, right? So whenever you have a binary response, it's golden because you can actually use empty symbols and filled symbols to encode that. And it's visually very stark. You have very high contrast visualization. So forget about everything else. Just look at that with empty and filled, and you can tell me something already. You'll notice that the filled symbols seem to be in the top right corner. Okay, they bleed down into the middle a bit, but top right corner, they're mostly filled. Bottom left corner, they're mostly empty. Okay, again, they bleed a little bit up into the middle, but beyond that, mostly empty. And so that kind of tells you that if you're in bottom left, it's not a good news. And if you're in top right, it is good news. And bottom left is low age and low weight, and top right is high age and high weight. And so by this we know pretty quickly that if you stay inside mum longer and you come out heavier, you've probably got a better chance of surviving, right? And look, isn't that obvious, right? Isn't that obvious? So, okay, what are the other things going on in here? Well, the symbols are called thermometers, okay? So they have a width and they have a height. They look like little rectangles and they've got these little wings. Now, what I've chosen to do here is to combine baby 4, which is that 1 minute APGARs, and baby 6, which is blood pH, as my 2 variables, which are the height and the width of the rectangles, okay? And then serve is survival code 01, okay? So the heights of these little rectangles are the blood pH, and the width of the rectangles are 1 minute APGARs. So what you should be able to see is in the bottom left of the plot, these should be narrow, right? Low 1 minute APGARs tend to go with not surviving. In the top of the plot, they should be wide. And you sort of can notice that. They go from being sort of narrow down here, with exceptions, of course, but they go to being mostly wide up here. With blood pH, it's much more subtle. They go from being short to being tall to being short again as you move up the plot. Because we know that the relationship with survival sort of starts low, peaks, and then drops again. And that's very hard to see. That's very hard to see. But in this single plot, it's a 2D plot, I've summarised 5 full dimensions of that data. Okay? So that's dimension reduction. I'm looking at a 5D set of information in 2D. I've got most of the information. Yes, it's a challenge to your brain because your brain's got to juggle these 5 things all at once, right? But you can part it out and you can say, look, I'm looking at the width now, I'm looking at the height now, I'm looking at empty versus filled. You can break it down and you can get most of that information pretty quickly. You won't get any information about interactions between the variables. Your brain's not that good, but it's not too bad. So as a first attempt at dimension reduction, this is pretty spectacular, right? We've gone from 5D down to 2D, and we've preserved a heap of information, okay? So that's pretty cool. Now, how do you do this in R? Right, let's build it bit by bit. Let's build it bit by bit. So the first thing you do is you draw the basic plot, but you leave it empty. It's a blank canvas at this point. Okay? How do you do that? You go plot baby 3, that's weight, that's age, that's the x variable. Baby 2 is weight, that's the y variable. When you go type equals n, you're saying don't put anything on the plot. Okay? Then label everything. The rest is just labeling. All right. Now, in order to create the empty symbols versus the full symbols, survival at the moment is a 0, 1 variable. I want to turn it into a true false variable. And the reason I want to turn it into a true false variable is that the thermometers command expects, if it's going to use empty and filled, it expects a true false. It doesn't expect a 0, 1. If it gets a 0 and 1, it's going to use those as lengths. Right? So it needs a Boolean. So the first, or a true false. So I'm going to take baby 1, which is survival. I'm going to ask, when is it equal to 1? So equals equals says, when are they equal? And if it is, true, and if it's not, false. So baby, comma, 1 equals equals 1 gives me a true when the baby survives and a false when the baby does not. So this is now a Boolean variable or a true-false variable. R also calls them logical variables. Okay? And then, so I do that, and then I come through and I add symbols to the plot. Now I have a lot of choice around symbols. Okay? So what choices do I have? Let's have a look. Help symbol. All right. Symbols, I meant to say. Okay, so the function draws symbols on a plot. One of 6 symbols are available. You can put in circles, you can put in squares, you can put in rectangles, you can put in stars, talk about them in a second. You can put in thermometers, which we've just looked at, and box plots. Okay, these are the 6 symbols you're allowed. I've never seen anyone put box plots on a plot and have it look good, to be honest. So you can do it, but don't look good, so I'd probably avoid that. The rest you can do. However, I will say, be careful, particularly with circles and squares. I'll tell you why in a sec. Okay, when you put in circles, you give it the radius of the circle. Okay? When you put in squares, you give the length of the side of a square. When you put in rectangles, it needs 2 things. It needs width and it needs height. So you give it a matrix with 2 columns. Right? The first is the width, the second is the height. Okay, easy peasy. Stars lets you draw little, they don't really look like stars, to be honest. They look like little octopuses with only 3 legs or 4 legs or 5 legs, right? However many variables you put in. So there's like a little centre bit and then there's stuff coming out from the centre, right? That's what stars look like. That's almost what it says, giving the lengths of the rays from the centre of the stars, okay? So that's if you want to encode more stuff. Sometimes pretty hard to interpret. Thermometers, a matrix with 3 or 4 columns. The first 2 columns give the width and the height of the thermometers. If there's 3 columns, the third is taken as a proportion. The thermometers are filled from their base to this proportion of their height. Okay. There are 4 columns. The third and fourth columns are taken as proportions, and the thermometers are filled between these 2 proportions of their heights. So it's pretty complicated. So we use 3 things: width and height, and then we fill them either 0 or 1. Okay, and then box plots. You'll notice if you look at the command itself, let's go over here, I put add equals true. That tells R to add it to an existing plot. So I've got a blank plot at the moment. If I go back to the plots section, I've got a blank plot at the moment. Add equals true says, put the symbols on the existing plot. Inches equals 1/12 will control the size of the symbols. Okay? So what I'm going to do is I'm going to show you, so I'm going to copy that. I'm going to paste it, but rather than just hitting return, I'm going to put inches equals 1 and make them too large. Okay? So prepare yourself to see something awful. Right? They're just too big. Right? So if you put inches equals 1, which is just too big. Now, there's actually information in this, believe it or not. Because they're so big, they sort of lump on top of each other, and so you get large areas of black and large areas of essentially white. And that tells you the same message as you got before, it's just that it looks ugly, right? So even though, you know, it gives you the information you want, it's ugly. So we can mess around with this and get the size we want, right? So there's the blank plot again, and there's the symbols again, and, you know, if I go inches is 1/6, they'll be smaller, so smaller than the original, bigger than what I showed you first up. Maybe that's a nice size, I don't know. So play around with that until you get something that looks good. Maybe they were too small before, so inches equals 1/6 would do that. So that's pretty good, okay? And that's the plot I end up with. Now, again, it's pretty ambitious, right? The thermometers allow you to encode lots of information pretty quickly. Now, circles and squares. Circles and squares. Well, the problem with circles and squares is that circles and squares are two-dimensional objects, but their size only depends on one number, right? So for a circle, it depends on their radius, and for a square, it depends on the length of its side, and that's it. So if you want to produce a circle or a square, you're creating a two-dimensional object based on a single-dimensional construct, which is a single number. Now, there's a problem there. When I show you a circle, how big is it, is a question I can ask you, and I'll get different answers from different people. So what I'm going to do is I'm going to come back and do this plot again. So I'll throw the plot up there on the page. I'll throw the symbols on, but this time I'm not going to use thermometers. I'm going to use circles. Circles equals, and I can just give it one vector. So we'll give it baby, I don't know, 4, whatever, okay? There are my circles, okay? And I've only encoded for one variable. Now, it uses the radius to encode it. So if I go from an APGAR of 2 to an APGAR of 4, the circle should get how many times as big? Twice as big, 4 divided by 2, right? How much bigger does it actually get? 4 times as big, right? Because when you look at a circle, you don't think about its radius, do you? You think about its area, okay? Because it's 2D, all right? So that's a problem. That's a big problem. And that creates what Tufte calls the lie factor, things that are apparently much bigger than they're supposed to be, okay? So I can be honest and say I would never use circles to encode a single object because you create two problems. The first is you create distortion because they're always the square of the radius in size perceptually, which will give you a ratio that's just wrong, right? You get the ratio of the squares of the radiuses, radii, not of the radii themselves. Same reason I wouldn't use squares. Now, what does Hans Rosling use? Circles everywhere, okay? So, we'll come back and talk about that later. So, I'd say never use circles, never use squares, because I think they give you a distortion. And this is where software lets you down, right? Because the people who wrote the symbols function thought, oh, wouldn't it be neat to have circles all over this plot? Yeah, sure, it's neat, it's just wrong. And misleading, and misguided, and all that stuff. But the people who write software don't care. They just want it to look pretty. Okay? So, you could do something, by the way, if you wanted to use circles. If you're desperate to use circles, what could you do? Square root? Take the square root of the radius, right? So I could do this. There's my empty plot. If I was desperate to use circles, desperate, I'd go square root of this. And you get actually the correct looking plot.
If we really use circle, how do we tell the difference between the survival or not?
At the moment you can't, because I'm only encoding for that other variable.
So you only can turn the baby 4, not the baby 6.
Correct. Yeah. Yeah. So there's a limitation there. There's a limitation. And that's the limitation of the symbols function. It doesn't let you fill them in. Thermometers are really the only way to get filled symbols with size elements as well. And that's why thermometers is what I showed you. We'd have to look at the help to see that. Blah, blah, blah. Where is it? Good question. Off the top of my head, I don't know. I never use them. I suggest we ask. Let's ask. Should we ask Google? Because I'm a big fan of Google. Got the hat, right? Are thermometers? Let's see what it says. Oh, that's nice. We're getting some pictures. Whoa! We're getting pictures of thermometers. Google, you failed me. Oh my God. Are thermometers symbols? Let's see what it gives me this time. Ah, here we go. Draw symbols. Very good. Oh, that's just the help. We can look that up in R. That's crazy. And then it's giving me stuff like this. Oh, forget it. Thermometer plots in R. Anyway, lots of people are asking. Let's have a look. Ugly. Oh, here we go. They don't seem to be using the little wings, do they? They're all the same. Very good. Not to worry. All right. So I'll have to look that up later. All right, let's do something a little bit different now. Let's be even less ambitious and just see how we might do empty and filled symbols if we don't want to use thermometers. So let me show you the plot that we're thinking about. So this is the simple plot we're thinking about. This is using a different approach. It's not using the symbols function, it's using the PCH option in plot. And the PCH plot option lets you draw different plotting characters. This is where we use something we know about plotting characters in order to produce empty and filled symbols. Okay? So here in this particular plot, the size of the symbol does not relate to anything. They're all the same size. Now, having said that, let me point something out to you that is very subtle but worth thinking about. Have a look at these symbols here. An empty triangle and a filled triangle that are quite close to one another. Does anybody think they're, well, let me ask, who thinks they're the same size? We know they're the same size, but who sees them as the same size? They don't look the same size. Which one looks bigger, which one looks smaller? Empty one looks bigger, right? And the filled one looks smaller. Black and white do weird things to your eyes, right? Now, you know, it's not often you can draw a lesson from fashion into statistics. But you know, in fashion they say always wear vertical stripes, makes you look thinner, right? This tells you if you wear dark colours, you'll look smaller. You wear light colours, you'll look bigger. Depends how you want to look, you can choose, right? This plays out here in graphics. You can see you've got the same size symbols, but they look different sizes. It's really interesting. Yeah?
I don't mean to rush you if you all get into it, but is there always an issue of filled symbols covering non-filled symbols?
Oh, yeah, of course. And the only way you can really deal with that is to try and make the symbols smaller. Not much you can do about it otherwise. Or make your plotting surface bigger. Yeah, but that's the same problem we always have in R, where you've got things sitting on top of one another. So the two approaches to fix it would be just to make your symbols smaller, or you could jitter the plot a little bit just to pull them apart. Either one is suboptimal, truthfully. Because when you make things smaller, old people can't see them, so that's a problem, like me. If you jitter it, jittering's interesting because jittering introduces random elements in both dimensions and shouldn't really change your perception of the plot, but humanity's ability to see patterns where none exist really ruins your day, because suddenly you see patterns that aren't real, and it's freaky. So yeah, but that's a good point. They're sitting right on top of each other, and you've got these three here, which are all empty, but the mass of them, because they're lumped together, makes them look less than empty. Yeah, so that's another subtle effect. The reason I mention these subtle effects is that, you know, as you look for graphics for part A of your project, right, subtle things are often the most damaging because they're happening without you even knowing it, right? And so you draw messages from graphics and it's just your eyes playing tricks on you. And optical illusions have a lot to say about how you perceive things. In fact, let me show you. This is pretty cool. Is anyone here likely to experience serious discomfort, maybe even a seizure, if you see things that are a bit funny, like shimmering lights and stuff like that? If you are, I'd advise you to look away. This is a web page from a Japanese psychologist. He's got a web page full of optical illusions. So this is his most famous one. It is called Rotating Snakes. By the way, that plot, or that picture is not moving. It is completely still. Good luck. And you know it's completely still because if you look at any particular part of it, it stops. But everything around it keeps moving. There's a reason for this. The way your eye works is it has a physical tremor, and this plot hooks into that. Okay, the rotating snakes. He's got a heap of them. I mean, when I scroll to the bottom, you'll just about fall off your chair. But this one here, if you move your head in and out, these things seem to move. Yeah. All those lines are, that's actually a grid, a square grid. It's not, there's no bulges. All the lines are straight, etc., right? Some of these are just freaky. And you say to yourself, oh, well, I can take it, there's only one page, right? None of these are moving, by the way. Yeah, it only goes up to page 60. Right? He's got 60 pages of this stuff. So it's just amazing. So here's his latest. I haven't seen these. These are his latest. Anyway, they've got a load, I guess. He's taken to posting little movies and stuff. But they all got that same kind of character, yeah. You might think, well, you know, why do we care about optical illusions? Again, remember that you know, the primary driver behind producing graphics is often to answer the question, compared to what? And when your eyes are making comparisons that are just wrong because of physical features of your eye, it really impairs your ability to make those comparisons. And optical illusions are really your eye doing something that physiologically it has to do in response to a stimulus, but which defeats your brain's decoding capacity, right? So it's really fascinating stuff. All right, so we're going to try and produce this plot. This is the empty versus filled. Again, I want to go through the R to produce it because it's a little bit complicated and there's a few lessons to be learned in here. So again, if I want to do this, I'm going to be using different symbols for different things. So I'm going to start with an empty plot, same as before. Plot age versus weight, type equals n, gives me the empty plot. Now, what I'm going to do in order to produce the two different symbols is not to use a symbols function, which does it all in one hit, but to put the symbols on separately. And again, this is a tool that you'll very often want to use. When you build plots, very often you want to build plots in layers, right? Put on one element, then put on another element, and so on, right? And so learning how to do this is really important. So here we want to put different symbols on whether or not the baby survives. So again, we're going to define this survival number. It's going to be a true or a false, okay? Now we're going to add the points. So first of all, we're going to add the points for the non-survivors, okay? How do I know it's the non-survivors? Well, I'm only picking out those points for which not survival is true, or in other words, survival is false, okay? So the exclamation point in front of a logical or Boolean variable reverses it. So exclamation point serve will give you a false when serve is true. So this will give you a false when the baby survives, okay? A true when the baby does not survive. So here we're only picking out babies that did not survive. We're plotting their weight, their age and their weight, and we're using plotting character 2, which is an empty triangle, okay? An empty triangle. So let's put those on. There they are. So that's the first part of my plot. Now I'm going to come through and put on the filled triangles, right? The ones for which the babies did survive. Same sort of syntax, except this time instead of exclamation point serve, it's just serve, okay? And now the filled symbols go on. Don't like triangles? Cool. You don't have to have triangles. I actually kind of don't like triangles. I don't really know why I did triangles. You could make them circles. If you start with PCH equals 1, you get empty circles. If you start with PCH equals 16, you get filled circles. Okay? Makes them slightly bigger. Slightly bigger. Makes them black. Okay? Don't know where I got that from. Now, there are some poor choices you can make too. Right? There are some poor choices you can make. Here you've got the empty plot. Now I'm going to put on PCH equals 3 pluses versus PCH equals 18. Oh, that's not what I wanted. Let's try that again. Sorry. PCH equals 3 and PCH equals 4. Pluses versus x's. Oh, I buggered that up. Sorry. Sorry. Got to learn how to use a keyboard, don't I? So these are I'll put the non-survivors on first. Apologies. Where are they? Here. PCH equals 3, plus symbols, and then I'll put the survivors on. PCH equals 4. All right. So you got to figure, right, on a Tuesday, either the lecture theatre doesn't work or the lecturer doesn't work, right? But the problem is, who do I call? Right? I can call a tech over to fix the projectors, but who can fix me? Oh my goodness. Anyway, so let's try that again. Sorry, apologies. Those are the surviving babies. Now let's put on the non-surviving babies. Okay, there we go. So it's x's versus pluses. All right? Why am I doing this? I'm doing this to show you that symbol choice matters, right? If I show you two symbols, and these are different symbols, right? One's a plus, right? And one's an X. And if I show you each of them one by one and I see which one's a plus, you'll get it right 100% of the time. And if I say which one's an X, you'll get that right 100% of the time too. You can recognise these symbols, right? If I put them both on a plot and I ask you what's going on in this plot, you can't do it easily because they're not different enough. They're different enough that you won't get it wrong if I ever show you one of them and ask you which it is. But they're similar enough that if I put them both on the plot, you can't easily pull them apart. They're not high enough contrast, if you like. Whereas empty versus filled is high contrast, and that's very simple, okay? And so symbol choice matters, and it matters by making the symbols different enough that visually you can make that instant judgment. Boom, boom. And that raises one of the other important things about visualisation. Visualisation has to be fast, right? There is no such thing as a good, slow visualisation because you lose people so quickly, right? Why don't we give people huge tables of numbers? Yeah, here's all the data. Work it out. Give them a big table of numbers, right? And if they complain, you go, but I've given you all the information. What the hell's wrong with you? And the reason is they bail out pretty quick. And they bail out because the comparisons are hard. There's a really wonderful book by a psychologist named Daniel Kahneman. It's called Thinking Fast and Slow. And I really recommend you read it. It's nothing to do with this course. It's just good reading. And it's all about how decision-making in humans has two kinds. The kind where you stop and think and the kind where you make decisions quickly. And you need both, right? In life, you have to make certain decisions quickly or you die. And so having that built-in capacity to make quick decisions, even though you might not be using all the information, is very important to your survival. But in visualisation, it leads you down the wrong path because those quick decisions don't work for you very well. Okay? So visualisation relies on fast thinking, not on slow thinking. Okay? And so visualisations have to hit you between the eyes, you get the message and you take it away with you. You don't stop and look and stare. If you're ever taking a graphic and you have to stare at it for 10 minutes to get the message, the person who created that graphic has fundamentally failed. Okay? And that's something you need to understand. Very important. Okay, so symbol plots. So the main lessons to take away from stuff today, and I know I've been going through this relatively slow, but there's a couple of reasons. The first is that you know, we're attempting something here that's pretty important. We're doing dimension reduction, high dimensions down to lower dimensional analogues without information loss. That's pretty cool. The second thing is I want to show you the R that does this, because I know that, you know, even at this stage of the semester, R is not necessarily something you live and breathe, right? So I want to go slowly through the R. So that's why I'm not rushing through this stuff. Okay, now I'm going to show you another set of plots, okay? And I won't have time to really talk much about them today. There's a lot of R to talk about. But I'll show you the plots and we'll talk through the plots and then we'll come back and do the R tomorrow, okay? So this is an example of something called coplots. Coplots, so the co in coplots stands for conditioning. It's a conditioning plot. One way you can deal with dimension reduction is to take one of the variables and essentially condition on it. So here I'm going to condition on 1 minute APGARs. So now 4 variables are going to be in play. Weight, age, survival, and 1 minute APGARs. And I'm going to divide 1 minute APGARs into low and high. So 1 minute APGARs goes between 0 and 9. So I'm going to go 0 to 4 is low, 5 to 9 is high. Okay. The reason I'm going to turn it into 2 is that I want to overload the circuits here, right? I'm just going to have, it's high contrast, low, high, okay? I don't have to divide it into 2. I could leave it as 0 to 9 and I could produce 10 coplots, 1 for each APGARs, okay? And you'll see later that's not a good idea. But high contrast always better. And then what I'm going to do is I'm going to produce, only for the low 1 minute APGARs, a plot of weight versus age coded for survival. And then for the high 1 minute APGARs, plot of weight versus age coded for survival. And I'm going to look at one plot and then the other, because I've got small multiples going on here, and I'm going to ask what's different between these two plots, because what's different is the impact of APGARs. Okay? So we're increasing the complexity, but now we've got 4 variables in play, and I'm still only in 2 dimensions. Right? So this is pretty cool. All right, so let's have a quick look at the plot. On the left is low 1 minute APGARs, on the right is high 1 minute APGARs. All right, tell me what's going on. Tell me what's going on. What do you see? What do you see? What's the difference between the two plots? The x-axis is different, so we could put them on the same axis. That'd probably be a good idea. So we could go ahead and do that and fix that. But for the minute, what do you notice about, well, let me ask you some leading questions, okay? So leading question number 1. In the first plot, what proportion of the symbols do you reckon are empty? Yeah, it looks to me, and again, quick visualisation, looks about 50-50, right? Looks like about half are empty and about half are full, maybe slightly more than half empty, okay? Now go to the right-hand plot. Does that proportion change or stay the same? Definitely changes, right? There's many more, well not many, there's proportionally more filled symbols in that right-hand plot than there is in the left-hand plot. If it was 60-40 empty to filled on the left-hand one, it's probably the opposite in the right-hand one. Probably goes from 60-40 to 40-60, and that's a material change between the two plots. And what that tells you is that when you go from low 1 minute APGARs to high 1 minute APGARs, survival prospects improve because there's more filled in that right-hand plot. So that's how you have to think about coplots. You look from one to the other and you ask what's different. What else is different? How do weight and age change as you move from left to right? You kind of notice in the left-hand plot that there's more stuff in the lower left corner, right? The thing seems to be shifted over to the left a little bit. Part of that's the range, which we can fix, but things seems to be shifted over to the left a little bit more, and that lower left corner is more populated. More populated, yes, by empty symbols, but more populated. You go to the right-hand plot, and it looks like everything's sort of been shoved up to the right corner, just a bit. Not a whole lot, just a bit. So we see two things going on here. we see that the weight-age relationship seems to move. It goes kind of from lower left and then a gradual shift to upper right. So as the APGARs grow from low to high, the weight and age shift from small weight, small age